I'll choose 4 polynomials in this vector space. This is a vector space of polynomials of degree 3 or less. These are my polynomials. This is the first one. This will be my second one. And this will be my third one. Actually, I said 4. Here they are. I need to test whether these polynomials are linear independent or dependent. And again, every time you do so, the test starts with the definition. The definition says we need to check whether a linear combination of such polynomials can be made into 0 while not every coefficient is 0. That's exactly what the definition says. Now we will see how it works in the context of polynomials. So I will substitute my polynomials. This is a substitution for P1. That's for P2 from here. This is for P3 from here. That's P4 and it's 0 on the right hand side. Pay attention. Here this 0 represents the 0 polynomial, the one which is identical 0 function. That's why it's not a bold-face. It's not a vector. I mean, it's not an n-tuple of zeros. So what you normally do with this, when you approach linear dependence, independence for polynomials, you rearrange. I mean, you expand all these brackets and you collect the terms with identical powers of x. So that's what I do here. You see, I collect all of the free terms, 1 lambda, 1, 2 lambda 2, 1 lambda 3. That's my free term. Then I collect all of the x terms, 2 lambda 1 here, no lambda 2, that's why it's missing, 1 lambda 3 in here, and 1 lambda 4 also in here. Then all of the x squared terms, no x squared term in here, that's why no lambda 1, 1 x squared term in here, that's why it's lambda 2, 4 actually x squared terms here, that's why it's a 4 lambda 3, and 1 x squared term here, that's why it's a lambda 4. And then the cubic terms, 1 from here, 1 from here, and that's it. All of them here. So I just rearranged. And then at this stage, you engage this property of polynomials, which you're supposed to know from the first year studies. The property says this. On the left-hand side here, what you're looking at is a polynomial. This is the first coefficient of that polynomial. This is the x coefficient, it's x squared coefficient of that polynomial. This is x cubed coefficient of that polynomial. What this identity tells us is that this entire huge polynomial is actually 0 polynomial, the one which is always 0. For polynomials, we know this only happens when every coefficient individually is 0. This is a stage where we engage this property of polynomials. If you're not using this property, you won't be able to finish this question, actually. This is a place where you refer back to the knowledge of polynomials you learned in the first year math. So if I engage this property, I will end up with individual coefficients being 0, which I can align into a system. That's my first coefficient being 0. That's my second coefficient. This is the second one. This is the third one from here being 0, and the last one here being 0. I have already arranged it in a way that you can see the columns of the corresponding augmented matrix. So we can proceed now to deciding whether this system is solvable and how many solutions it has. So you extract this augmented matrix from the system. You extract this augmented matrix from the system. You take it to the row echelon form. As before, I hide all of the intermediate steps. You can recover them in your own time, and this is the corresponding augmented matrix. Sorry, this is the corresponding row echelon form, I should say. If you come up with the proper chain of row operations, you will be able to convert this matrix into this row echelon form. By looking at this row echelon form, I can spot 4 leading columns. I can spot none or no non-leading columns on the left-hand side, which tells me that the only solution to this system of linear equations is the zero solution. Hence, my polynomials are linearly independent. Again, let me emphasize this step in the entire solution, this step here. This step, I mean, normally when you make your own proofs or read somebody else's proofs, every single proof has this feature. There is no single proof which actually fully self-contained, fully built up from scratch. Every single proof has a reference to some other knowledge, which is framed as a theorem or some other result, or in some other way. Every single proof has these features. They always reference something else. You never have a self-contained proofs, never ever. And it's a good quality of a good mathematician to be able to spot those steps in the proof where this reference is made. In this one, that's the step which I just emphasized. This is a step where we're referencing something from the past. Our knowledge of polynomials. Because we know identical, I mean, if polynomial is identically zero, that's exactly what this identity tells me. It means that it's true. This identity holds for any x, for any argument x of your polynomial. This only happens when every coefficient is zero.